we're doing problem 4 from section 4.4. In this case, we have a linear system with coefficients. The vector x has two components, x1, x2, and we'd like to solve for the initial condition when at time t equal to 0, x1 is 3 and x2 is 0. We're going to solve this using linear algebra techniques, and so the first thing we want to do is find the eigenvalues for this matrix. The characteristic polynomial is this, lambda squared plus 5 lambda plus 4. And for 2 by 2 systems, it's actually fairly easy to write down this polynomial. The coefficient in front of the linear term is minus the sum of the diagonal entries. The sum of the diagonal entries is called the trace, and this is minus that sum. And the constant term is the determinant here. Minus 2 times minus 3 is 6. Minus 1 times 2 is 4. And so that's our characteristic equation. And we find the eigenvalues lambda 1 equal to minus 3 and lambda 2 equal to minus 1. In terms of the eventual solution, lambda 1 equal to minus 4 corresponds to a factor of e to the minus 4t. And lambda 2 equal to minus 1 corresponds to a factor of e to the minus t. Those factors will be multiplying vectors, and those vectors are the eigenvalues corresponding to this particular, the eigenvectors corresponding to those particular eigenvalues. So for lambda 1, we find that u1 is 1 minus 1, and for lambda 2 minus 1, we find that u2 is 2, 1. It's good once you do the calculation to actually check. So let's do that. If I take 1 minus 1 and apply the matrix to it, I get minus 2 times 1, which is minus 2. 2 times minus 1, which is minus 2. Altogether minus 4, and that is minus 4 times 1. When I look at the second row, I get 1 times 1, which is 1. Minus 3 times minus 1 is plus 3. 1 plus 3 is 4, and that is minus 4 times minus 1. So this vector really does satisfy that when I apply the matrix to it, I get minus 4 times the vector that I started out with. So that checks this one. Checking this one a little faster, minus 4 plus 2 is minus 2, which is minus 1 times 2, and 2 minus 3 is minus 1, which is minus 1 times 1. So that also checks. And now I'd like to first match the initial condition and then write down the solution that we get using those exponentials and the linear combination of the eigenvectors. Remember, we had the initial condition 3, 0, and we have the eigenvectors 1 minus 1 for eigenvalue minus 4 and 2, 1 for eigenvalue minus 2. We'd like to write this initial condition as a linear combination of the two eigenvectors, and doing that, we find that C1 is 1 and C2 is 1. It's a system of two equations for those two numbers, C1 and C2. And let's just check. If I take 1 minus 1 and add 2, 1, I get 3 and 0, so that's correct. And what does that mean in terms of the solution? It means that e to the minus 4t multiplies 1 minus 1, and e to the minus t multiplies 2, 1. Again, the coefficients are 1 in front of here and 1 in front of here. And that's the solution in vector form. If you want to see what x1 of t and x2 of t are, you write this out in terms of the components. And so we get e to the minus 4t times 1 plus e to the minus t times 2. So e to the minus 4t plus 2 e to the minus t is x1. And similarly, you can find x2.